Hello again. Today we continue with computer system architecture course, and our topic is instruction formats. In the previous two videos we discussed general register organization and stack organization. According to the stored program concept, both instructions and data are stored in memory. In order to execute an instruction, we should bring it to the CPU, fetch it, then decode it, and after that execute it. And we continue to the next instruction. The most common fields in instruction formats are the operation code field that specifies the operation to be performed. For example, addition, subtraction, multiplication, division, etc. An address field that contains the address or addresses of operands. And a mode field that specifies the way the operand is determined. Regarding the operation code field, if we want the computer to perform, for example, 64 operations, then we need at least 6 bits to encode each operation. Next, regarding the address field, if the size of memory is 2 to the power n locations, then we need n bits to address any location in memory. So for addressing each operand, we need n bits. And regarding the mode field, in the basic computer, we have only 1 bit I for direct, indirect addressing. But for example, if we have 8 addressing modes, then we need 3 bits to encode each addressing mode. There are 2 contradictory requirements to the size of instruction. The first one, the instruction must contain all the necessary information regarding the operation to be performed and the addresses of the operands involved. To provide all this information, the instruction size is increased. And the second, since the instructions are stored in memory, it's preferable to have a small or not large instruction size. It's good if the instruction can be stored in one memory location or a small number of locations. In general, we would like to have the following information in the instruction: the operation code, address of first operand, address of second operand, address of result, and address of next instruction to be executed. And this format is called for address instruction format. If we have 64 operations, then we need 6 bits in the operation code field. And if the memory size is 64 K locations, then we need 16 bits to address any location. So here we need 16 bits, 16, the result in memory 16, and the address of next instruction is 16 bits. And the total size of the instruction is 64 plus 6, which is 70 bits. And this assuming that we have only 64K locations. If we have, for example, 1 megabyte locations, then we have here 20 bits. So we need for these fields 80 bits. So the total is 86 bits. And this is a very large size. And this for address instruction format was never used. Now, how to reduce the size of the instruction? We can get rid of the address of next instruction, and this was done by introducing the program counter. The program counter is a register in the CPU used to hold the address of the next instruction to be executed. So after fetching the current instruction, the content of the program counter is incremented by 1 to point to the address of next instruction. In this case, the address of next instruction field is not required in the instruction itself. Now we have a 3 address instruction format. Address of first operand, address of second operand, and address of result. So the operation is performed on the 2 operands, and the result is stored in the result field. For example, the instruction add R1, R2, R3. This is a 3 instruction format that adds the contents of register R2 with R3, and the result is stored in register R1. So here we have 3 fields in the address field. We can reduce the size of the instruction by getting rid of the address of result and store the result in the address of first operand or on the address of the second operand. And this format is called 2 address instruction format. Since we have only 2 fields here in the address part, for example, the instruction add R1 X. According to this instruction, the content of the memory location addressed by X is added to the content of register R1, and the result is stored in R1. We can reduce the size of the instruction by using one of the registers as an implied register for one of the operands, for example, the accumulator. In this case, we'll have 1 field for the address in the instruction, and this format is called 1 address instruction format. For example, the instruction add X. Here we have only 1 field for the address X, and according to this instruction, the content of the memory location addressed by X is added to the content of the accumulator, and the result is stored in the accumulator. Next, can we have a 0 address format? The answer is yes. In the last video, we discussed the stack organization, and it was shown that if we represent the expression in a reverse Polish notation, then in the address field of operations, we do not have to specify operands. So if we have in the instruction just the operation code field without any address fields, then the address format is called 0 address instruction format. For example, the instruction add adds the top two locations of the stack, for example, A and B, and stores the result at the top of the stack. Here we haven't added this field. And in this notation, we'll have add this field only with the push and pop instructions. To push an item in the stack, we need to specify its address, and to pop an item from the stack, we also need to specify the address field. Most computers fall into one of the three types of CPU organizations: single accumulator organization, general register organization, and stack organization. An example of single accumulator organization is the basic computer. The instruction format uses one address field. Again, add X. And as I mentioned, here the memory location addressed by X is added to the accumulator, and the result is stored in the accumulator. General register type computers employ 2 or 3 address fields in their instruction formats. For example, add R4, R3, R2. Here is a 3 instruction format. The content of R2 is added to the content of R3, and the result is stored in R4. And we can use, for example, add R1, R2. 2 instruction format. Here the content of R2 is added to the content of R1, and the result is stored in R1. And even with memory locations, for example, add R1, Y. Here the content of the memory location addressed by Y is added to R1, and the result is stored in R1. I mentioned that computers with the stack organization would have push and pop instructions, which requires an address field. But operation type instructions such add, sub, mul, etc. do not need an address field. The operation is performed on the 2 locations on the top of the stack. To illustrate the influence of the number of addresses on computer programs, we will evaluate the arithmetic statement x equals a plus b multiplied by c plus d using 0, 1, 2, or 3 address instructions. We will use the symbols add, sub, mul, and div for the arithmetic operations, move for the transfer type operation, and load and store for transfers to and from memory and accumulator register. And we will assume that operands A, B, C, D are in memory, and the results should be stored in the memory location X. First, 3 address instruction format. Here we can directly add A and B and store the result in one of the CPU registers, for example, R1. Next, we can add C and D and store the result, for example, in register R2. Next, we have to multiply the contents of register R1 and R2 and store the result in X. So now in X, we'll have the result of evaluating this expression. The main disadvantage of 3 address instruction format is that it requires too many bits to specify the 3 addresses. In the two address instructions, we can first move A, for example, to register R1, then add B to R1. So in R1, now we have A plus B. Next, we can move C to register, for example, R2, and add D to R2. So now in R2, we have C plus D. Next, we have to multiply the contents of registers R1 and R2. So now in R1, we have A plus B multiplied by C plus D. And next, we can store the result in location X. Next, one address instructions. We have only the accumulator. So we can load A into the accumulator, add B to the accumulator. So now in the accumulator, we have A plus B. And since we need the accumulator in the next computations, we can store accumulator in location, for example, sum 1. Next, we can use the accumulator by loading C, add to it D. So now in the accumulator, we have C plus D. And we can multiply this value by sum 1. So in the accumulator, we have C plus D multiplied by sum 1, which is really A plus B. And we can store the result in location X. And in the zero address instructions, we are going to use the stack. First, we can push A into the stack. Next, push B. So now in the stack, we have on the top B. Do you see here no address field? Now in the stack, we'll have A plus B. Next, we can push C here, push D here, and perform the add. So in the stack, now we'll have here C plus D. Next, we can perform the multiplication, mul. So in the stack, we'll have A plus B multiplied by C plus D. And now we can pop the contents of the stack into location X. Next, RISC instruction. RISC stands for Reduced Instruction Set Computer. The instruction set of a typical RISC processor is restricted to the use of load and store instructions when communicating between memory and CPU. All other instructions are executed within the registers of the CPU without referring to memory. So we have only two instructions, load and store, to communicate between memory and CPU. And all computational type instructions are performed in the CPU. The idea of RISC architecture is to reduce the execution time by simplifying the instruction set of the computer. And memory access is limited only to load and store. So in order to evaluate the expression, we have to load the operands into the CPU. For example, A to R1, B to R2, C to R3, and D to R4. Next, we can add A and B, which is in R1, R2, and store the result, for example, in R1. So now in R1, we have A plus B. Next, we can add R3, R4, and store the result, for example, in R3. So in R3, now we have C plus D. Next, we can multiply the contents of R1 and R3 and store the result from R1 to X. So now in location X, we have our expression. And we will come to RISC architecture later in this chapter. Our next topic is addressing modes. For today, that's all. Thank you.